And then finally, let's investigate a little bit the uncertainties. You remember that we have two kinds of uncertainties. First of all, we have a fitting error. This is exactly this standard error of prediction. And we can calculate the uncertainty by just using t-distribution because we have a sample size is small. Then for a certain confidence level, we can always calculate this fitting error as a plus minus t times s standard error. However, we also have, especially if sample size is small, we have uncertainty from the position of the line. So the regression coefficients are also not quite certain, right? So the position of the regression coefficients varies, and we don't know the exact regression coefficient. So this term in this formula gives us this uncertainty. So what I want us to do is to make these two plots, this one and this one, where we have both uncertainties together, or where we have only one, but only a particular one. For example, only uncertainty for the lines. Okay, we will simply use this the formula that is shown on this slide, and try to calculate it. And that's my idea. So we'll take a lot of x values, starting from probably 15 and ending with maybe 50 or 55, and then for each of the value, I will calculate two positions. It's the smallest possible uncertainty and the largest possible uncertainty. And then I will show these two lines using these values. Okay, so let's do that. So first of all, we need to find out several things. You see, we need to know n, we need to know t value, we need to know standard error, and then we also need to know the average of x and the variance for x. So let's do the calculations. Let's calculate the t value first. So the t value is its ICDF function for 0.975. I will take the right tail for this, the right part of the two tails. And then the degrees of freedom is 31 in our case, right? So that's the t value. Then if you look at the t value, you can see it's exactly the one we used in the lecture. It's 2.04. Okay. Now let's calculate the standard error. We know the standard error already, right? But let's calculate it manually once again. You remember that standard error is calculated by taking a difference between the real y values and the predicted y values. Then you square these differences, and then you take a sum of squared values and divide it to degrees of freedom. Okay. We already have the difference. It's our e values, right? So we can do it like this. Standard error is a square root of sum of squared differences divided to n minus 2. In our case, n minus 2 is 30. I will just write 30. And then I should get the same standard error as we have. So you can see that it's indeed 4,227. Okay. So now we have standard error. Let's calculate the average for x. So it will be just mean of all, in this case, age, right? So mean the age. Then we have the standard deviation for x. H. Then I think that's everything we need. Right? So now we can calculate. We need to generate a sequence of h values. So I will use xx for that. So I say generate a sequence. Start from 15. Actually, the smallest h we have is 18. So I can start with 18, of course. Then adds with 55, and then I will generate, for example, 100 values. And then I calculate the predictions using our model. Data frame h2. So if you see, I have the vector with also with 100 values that corresponds to the values in x-axis. Now I can calculate the boundaries. I will start with calculating boundaries only for that takes into account the position of the regression line, and then I will also add boundaries that takes into account both the fitting error and the sampling error. Okay. So I'll just take up and down. So up, the upper boundary, it will be my predicted value plus t times standard error times the square root of, well, first of all, it's 1 over sample size is 32 plus then our x values minus the average x, square it, and then I divide it to the standard deviation of x, square it, it's a variance, and then times n minus 1. So I just use the formulas we discussed recently. Then to make a lower boundary, I do the same, but I subtract these values. Okay, and then of course it's a lower boundary. So run this, and it should be sx. Oh, of course it's sx. That's a mistake. So now I can probably calculate it, n I'll just use 31 here to simplify it. Okay, 31. Now it should work. Yes, it does. So I have 100 values for the upper boundaries, and then I have also 100 values for the lower boundaries. Now I can make a plot. I make a plot first for the real values, XX and YP. For the real values, meaning for the ones that we have, of course. It will be age, it will be income related to age, and then data equal to DA. So that's my real data, income and age for the real data. Then I add the model, AB line, and the model I will make it as a red line. So that's the AB line, of course, AB line. So that's the model, and then I will add also this, make the line plots for the boundaries. So I add lines, and then I have this XX and lower boundary. I will make it also red, but dashed line. So that's the lower boundary. You can see it has the same shape as I showed you in the slides, and then we add the same for the upper boundaries. Okay. Upper boundary. So this two lines shows you uncertainty right from the uncertainty in regression coefficient. So we don't know the exact position of the line, we don't know the exact orientation of the line, and that brings uncertainty to predictions, right? That's why we have this predicted y values a bit uncertain. Okay. Then let's take into account both uncertainty from the position of the regression line and uncertainty from the fitted values, so the standard error. So I'll just copy and paste these two. Then I will call it like F up, F low means full uncertainty. Then the only thing I have to change is to add 1 here. So now I also take into account the fitting error. Then I can just add these lines as a full and full here. Then let's make them dotted lines so we can differentiate them. Okay. So that's the uncertainties from the both from the sampling error and from the fitted error. And then you can see indeed that all my values align inside this is uncertainty interval, right? So we don't have any values outside that. And that's what we calculated for 95%. Of course, we still have, if we have more points, we still have a chance that some points will lie outside this range. Okay. So that's how to visualize the inference, the uncertainties in the simple linear regression.